So in this video, we will discuss a tiny practical example on LightAutoML and how to use it for building machine learning pipelines. So let us proceed to the notebook. We start as usual with the installation of required libraries, and the LightAutoML framework is installed very simple. We use our common pip package manager, common for Python. We install LightAutoML as every other library, and then it is installed and ready to use. So then we import different Python libraries which are required in this notebook. So everything starts with common Python libraries such as OS or time or requests. Then we import different libraries which are essential for data science, such as NumPy, Pandas, Sklearn, PyTorch. And finally, we import different instances from LightAutoML. We will require TableRAuTML and TableRUtilizeAuTML presets, and a task object, which we'll discuss a little bit later. Then we fix some constants for reproducibility. This is the random state and the number of threads which would process our data. Then we pass these parameters to the required libraries, such as NumPy and PyTorch. Then we do the loading of data, just some arbitrary data from the internet, stored as a pandas data frame or as a comma-separated value file. These few cells of code are required to download the data and load it to the notebook. And then we finish with this pandas data frame, which has quite a lot of different features, both numeric and categorical, and I think even binary. So quite many features. There are even some missing values. So actually this is like real data, which might be quite challenging to work with. So we'll test our LightAutoML framework in real conditions. This is the data set for binary classification. So here's the target column, which stores a binary variable. And then we proceed to splitting the data to training and testing. We just used common train test split function from Sklearn, selecting 20% of the sample as for testing. We also use stratification so that our binary class was split in a proper way, and fix the random state of the split for reproducibility once again. So finally, our data is splitted. We're ready to train our models, and we see that the size of the training set is about 8,000 samples, having like 122 different columns, one of which is our target column, and the testing data set has 2,000 objects. So then we are ready to create and fit our TableRAuTML, but first of all we need to specify which task to solve. So as I mentioned, we have a dataset for binary classification, so let us state that this task is binary classification. We pass this required field to the task object and say that this is we're going to solve the binary classification task. Moreover, we specify that we want to use log-loss function and the ROC area under curve metric to qualify our models and select the best one. Then we need to specify the feature roles. The only required feature role is target. So actually this is our target variable to predict our column with target. And we also want to drop several columns, actually only one in this case. As usual in machine learning, we don't want any kind of identification number to be the feature that we are using for fitting our models, because it's like very easy to overfit on this feature because this is unique for every sample in the dataset. Then we specify different parameters of fitting. So we would like to use 5 folds for cross-validation and specify the total timeout to be 30 minutes. This one is stated in seconds, so we take 16 seconds in a single minute and multiply them by 30. Then we create the TableRAuTML instance. We specify the task to solve, the total timeout, which is 30 minutes in our case, and the number of threads to process our data. There are also a few reader params, such as, again, the random state, the number of cross-validation folds, and number of threads processing our data. Then we are ready to fit the AutoML pipeline, and we can see quite a few logs which are outputted by this cell. And so we can see that the overall fitting time is 1,800 seconds, which is actually equal to the 30 minutes. We have 4 CPU cores processing the data and 16 gigabytes of memory available. So here's our training sample consisting of 8,000 of objects. And here we can see the log of different models which start to fit. We're starting with the linear model, which is a logistic regression in our case because we're solving binary classification. And this is the model of the 0 level, the same as other models, which we'll discuss later. So here is the area under curve score for this model, 33.5 approximately. And then we are proceeding to the gradient boosting models. So this is a LightGBM implementation. There are 2 options of these gradient boosting, one with default hyperparameters and the other one with optimized hyperparameters, which you can see here. After we've finished fitting the LightGBM, we also try the CutBoost, a different library for gradient boosting, and the same we have the one with default hyperparameters and the one with tuned hyperparameters. So overall we consider 5 models here. And then after these 5 models are fit, we proceed to the blending stage, which combines the 5 models we fitted earlier. So here are the weights for these 5 models, which are optimized by the Blender object. And then we finish up with this configuration of the model. So we have 5 models. 4 gradient boostings of 2 libraries that are implementing gradient boosting and either with default hyperparameters or with the optimized hyperparameters, and a linear model. So each basic model consists of an average 5 average models, which are averaged by different folds of training sample. As we splitted the training sample into 5 folds, we have 5 models to average here. And then these basic models are accumulated and aggregated by the Blender. So here are their coefficients, and the model, the Blender takes these basic models and averages their outputs by the following using the following weights. So we spent around 6.5 minutes to fit this AutoML pipeline, and here is the description of our pipeline, like the same information about blending and the weights of this blending for these models. Then we can generate prediction for our testing data and calculate the metrics. So here we have our area under curve. So the first line here of this output is the score of out-of-fold predictions for the training set. And the second line is the predictions for the holdout test set, which is around 73.44. Notably, to mention that we spent around 6.5 minutes for fitting our pipeline, despite the fact that the overall timeout was 30 minutes. So this is quite weird. And we actually want to utilize all the time available to get the best models. So that is why we would like to use tabular utilized AutoML preset. Actually, what it does is to take a different tabular AutoML with different random seeds for cross-validation and different configurations, and blends this model. So easy as that. We'll spend more time and fit more models to get the better quality. So the same to the simple tabular AutoML, we initialize our tabular utilized AutoML with the same parameters and then start fitting. So here is the logs, which are like quite the same to the simple and common tabular AutoML, but they for utilized version. So we'd better proceed to these description of the models. So here finally we can see that there are 3 basic AutoMLs which are blended by our utilized tabular AutoML. So here in the first basic AutoML we have all 5 models, 4 gradient boostings and a single linear model, which are averaged. Their outputs are averaged with these weights. We also have 2 more AutoMLs, each of which consists of just 4 models. We don't see here cut boost with default hyperparameters, probably because this model was too weak and the Blender decided to throw it out, just to use 4 of the rest models. And finally, all these 3 AutoMLs are averaged. Their predictions are weighted with these coefficients, like 17.5, 13, and 69.5. And this is our overall model. As the same as for the simple tabular AutoML, we can generate predictions for the training set and measure the area under curve for these predictions. So for the testing set, we have 33.55, which is slightly better than we had for a single tabular AutoML, which was 73.44. So, for example, you can just leave the model to feed for a weekend and then return back on Monday morning and see that everything is ready, and you have a fine model which used all the weekends to feed to the data. So that was an example how to take your AutoML and make it work out of the box. So pretty simple, and works like for any arbitrary data. So it is very easy to use tabular AutoML. Thank you for your attention.